In this video, we're going to talk about some useful distributions. You see two sets of distributions on this slide. On the left are 6 distributions that are going to be really useful when you have no information at all, or you have limited information. Typically, these would be distributions you would use when you have limited or no data. They're defined by the shape of the distribution. On the right, you see 4 distributions mentioned that come from the mathematical or theoretical formulation here. Now, as we move through these distributions, we're going to be using a simple mind example, if you will, and that is, imagine a hurricane barrier, and there is a vessel that has to pass through this barrier, and we're going to be interested in how long it takes a vessel to get through the barrier. Okay? So let's begin with the uniform distribution. The uniform distribution is useful to use when you're dealing with a lot of uncertainty. So let's imagine our example here. How long does it take to pass through the barrier? How long would it take a barge to pass through this hurricane barrier? And your response might be, we don't have any data on that. So then I might say, okay, so it's between plus and minus infinity. And you'd say, no, we can do a lot better than that. It's going to be at least some positive amount. We can eliminate all the negative values. And it's not going to take forever. And so we can estimate some minimums and maximums. And that's what you do with a uniform distribution. You estimate a minimum and a maximum value. And that gives you a flat distribution. And so it's going to be convenient at times to talk about uncertainty as a shape. And this is a picture of our uncertainty about how long it's going to take a barge to pass through a barrier here. Okay, and what we have, if you look on the right-hand side at the grid, there's a minimum of 5 minutes and a maximum of 12 minutes. But we don't know anything else. Any time in there between 5 and 12 is as likely as any other. And that's a characteristic of the uniform. Any value is as likely as any other, okay? So when we talk about how many minutes will it take a barge to pass through the hurricane barrier, we're saying it's between 5 and 12. And if you're asking, do we know anything else? The answer is no. That's all we know. And so this distribution comes up frequently when you're dealing in situations where you have no collected data. The beta general is a really handy distribution. It's handy because it's a shape shifter. Now, we're talking about the same issue. How long will it take a barge to pass through the barrier? So we would use the same minimum and maximum, 5 and 12 minutes. But how likely is a short transit versus a long transit? We might have different beliefs about which values are most likely. We might say, it's perfectly random and use a shape like you see at the top, where we're saying somewhere in the middle is most likely. If we're near the mean of those two values, that's the most likely. And down on the bottom, you see this is a distribution that we would use if we think it's more likely that it's going to be closer to 12 than to 5. So you have two shape parameters here. You would put in the minimum and the maximum, and you have an alpha 1 and an alpha 2, and they affect the shape of the distribution, how that blue shape covers the number line from 5 to 12. So I'm going to suggest you just play with those alpha 1 and alpha 2 parameters and see how they change things. Okay? You use this distribution to reflect your subjective judgment about a value. So we don't have data, but we have some reason to believe that it takes vessels closer to 12 minutes than to 5. 5 would be really unusual. You'd need perfect conditions on the water. You'd need an experienced pilot on the tug, and all these other things that don't occur that often. Typically, there's something or other going on that makes the passage a little bit longer. So you're using judgment. You're saying, yeah, that feels right. So you shift the distribution until you get something that represents your beliefs about the values, and that's what you run with. The triangle distribution is another commonly used distribution, and it has a slight improvement over the uniform distribution because it's based on a little bit more information. So imagine that you have done some simulations for barges moving through the barrier, and the simulations reveal that the most likely value is 7.3 minutes. Now, the most likely is not the mean, it's the mode. It's the value that happens most often, or that is most likely to happen. But now we have three pieces of data. We have the minimum, which is 5, the maximum, which is 12, and a mode, which is 7.3. So imagine that we're on the number line, and I grab 7.3 and I raise it up. I raise it up to the point that you see there. And then I take my ruler and I connect the dots. 5 to that peak, and then that peak off to 12. And that's essentially what a triangle distribution is. Now, the math is a little bit more sophisticated than that. But essentially what you have here is a uniform distribution plus a most likely value. It's a very handy distribution to use. The Pert distribution is another handy distribution. It uses the same three pieces of data that you use for the triangular distribution. But the difference is, as you can see here, the blue distribution is the triangle from the last slide, and the red distribution around it is what the Pert distribution would look like. Now, this is not literally how it works, but instead of using a ruler, if I used a French curve to connect the three dots, I might get something more like the red distribution. And you'll notice that in this particular example, there's a greater likelihood that lower values will occur. Notice how the red line is above the blue line. But there is less likelihood that bigger numbers will occur. Notice that the red line is below the blue line. And so sometimes you'll want to use a Pert, sometimes you'll want to use a triangle. But as you're learning the software, play with it. If you use a triangle, throw a Pert in there with the same data points and begin to get a feel for how they differ. When you're trying to represent subjective judgments, sometimes it can be helpful to say, you know, I'd like to see a little bit more likelihood of those low values. That's a perfectly okay thing to do when you're working with judgments. The Trigen is a nice distribution to use when you're not really sure what the minimum and maximum values might be. So sticking with our same example, how long does it take a barge to pass through the barrier? You would enter the minimum 5, the maximum 12, the most likely 7.3. But now what we're going to do is we're going to enter a couple of other values along with that. Instead of calling it the minimum and the maximum, they call it the bottom and the top of the distribution. And then there is a bottom percent. And here you would enter a value. You might say, well, 5% of all the values could be below my minimum or my bottom of 5 minutes. So if you think it's 5%, you would enter a 5 there. If you think there's only a 1% chance it would be less than 5 minutes, you would enter a 1 there. And similarly, for the top percent, you would say, okay, there's a 10% chance that it could be more than 12 minutes. Or there's a 20% chance it could be more than 12 minutes. These percentages don't have to be symmetrical. They reflect your judgments about the level of confidence that you have in identifying the minimum and maximum values. Okay? The beta distribution is a variation on the beta general. It's handy because it's specifically for the 0 to 1 interval. So the beta distribution could be frequently used for estimating things like probabilities. If you're providing subjective probability estimates, they are going to be constrained between 0 and 1. So you can use this for probabilities and for parts of a whole thing. If you're talking about how much of a wall has spalling, you can use this. It's between 0% and 100%. Like the beta general, it has two shape-shifting parameters. And so you see a couple of choices here in the slide. The first one that just is kind of the default value for the beta generation, for the beta distribution, excuse me there. And then down below, we have a differently shaped distribution. You can change the shape shifters to reflect your judgments about the distribution values. I've switched the example on you here a little bit because how long does it take for a barge to get through the hurricane barrier doesn't really apply for a beta distribution. So once again, the beta is really good for estimating probabilities and parts of a whole. You have the 0 to 1, and then you play with the shape parameters basically to say, that's pretty much what I believe. This is what we think is true. Okay, so you're doing this stuff not with data, but with your judgment. The binomial distribution is really important, and it's really useful if you're going to be developing event trees and things like that. And here's the way it basically works. It has two parameters. It has n, which is the number of trials, and it has p. P is a constant. It's an identical probability for each trial. So here I'm talking about the number of elisions. An elision is when a barge or a vessel strikes something that's fixed in the channel, like a hurricane barrier. But let's make it simpler here. Let's talk about games, the number of games that you're going to play. And if we had, let's say, because it's what we see on the screen here, if we had 5 games in the top distribution, each one of those games you would have the same probability of winning. Okay, so we define a success or a failure. Typically, we talk about success when we're identifying the probability P. So we want the probability of success. If there's a 20% chance you're going to beat this team, there's an 80% chance that you won't. So we're using the success probability, the 20% instead of the 80. Okay, now let's flip back to our number of elisions here. So we have, in this example, we have an n of 125. So in that top graph, you're only getting a little bit of the picture here, okay? And you can see that the probability changes, but you would set a probability that would be identical for each one of those 125 barges going through the hurricane barrier. Each one has some probability of successfully having an elision. So we talk about success, even though it's not a good thing to have an elision. This is the thing that we're interested in, and it's what we define as success. What the graph is showing you is the probability of specific numbers of successes. So if we have 125 barges, we could have no elisions all the way up through 125 elisions. And so what you're seeing there is the probability of no, 1, 2, 3, and 4 elisions. Okay? You would change the probability or the n, the number of trials, to reflect your situation. This is really useful for failure estimates. If we're talking about n is the number of years that you live in a floodplain, let's say that you live there for 75 years, and P is the probability of having a flood of, in the 10-year floodplain or greater, a 10-year or greater flood in any given year, that's going to be 10%. And so you can use this to estimate the likelihood of 0 through 75 floods. So the binomial is a little hard to pick up on one slide, but fortunately we spend some time with it elsewhere in the course. Now we're finished with those subjective judgment types of distributions, and we're going to move on to things that are more theoretical and mathematically based. We'll start with the normal distribution. It has 2 parameters. It has a mean and a standard deviation. And we've left the time to move through the barrier behind now. Many to most biological variables are normally distributed. If you take a human being, intelligence, height, length of the forearm, any kind of distance between your eyes, any kind of biological measurement that you can imagine, these tend to be normally distributed. There are a lot of values and variables in the world that are single peaked and symmetrical. It's as likely to be above the mean as below the mean. The normal distribution is really handy when working with sample statistics. The central limit theorem makes it extremely useful for sample statistics. It's a very useful distribution. If you have a variable that is the sum of many other variables, like a cost estimate, that's the sum of many different costs. A cost estimate is likely to be normally distributed. So the normal distribution comes up quite a bit. The Poisson distribution is kind of like a normal distribution for discrete random variables. It gives you the number of events in a specified interval. The parameter that you'll find when you open up at risk is lambda, and lambda is really the mean. It would be the average number of barges per month, the average number of elisions per year, the average number of cracks that you'll find in a square yard of concrete, the average number of flaws in a Persian carpet or anything like that. It's the average of some countable thing per something. So the specified interval can be time, it can be space, it can be the average number of cracked eggs in a dozen eggs. It can be anything that you imagine that is the number of events in a specified interval. It comes up a lot in navigation. For example, it could be the number of barges per tow, the number of tows per month, the number of vessels per day, and all of those kinds of things that you encounter in navigation analysis. The exponential distribution is useful because it measures the time between events. Now, you'll notice the first bullet says in a Poisson process. So if you happen to have for that Poisson process the number of barges per month, then the exponential distribution would be a good way to express the time between barges per month. If it's the number of customers during the lunch hour, the exponential would have would be the time between customers entering your store during the lunch hour. It has one parameter, beta. Beta is the mean, but for the exponential, the mean and the standard deviation are identical. This is a great distribution to use for wait time. How long between patients in a doctor's office? How long do you have to wait? How long does a barge have to wait? So because it's used for wait time, it's a great distribution for queuing theory and things of that nature. So if we're talking about, so these are some handy distributions to use. My advice to you is make sure you know the uniform, the triangle, the Pert, and the binomial really well before you leave this course. Just ignore that last bullet there. It's left over from something that I forgot to erase.